Hello, this is a presentation recorded for the IEEE Conference on Decision and Control 2020. I'm Chong, and I'll be presenting our paper on a secure state estimation algorithm for nonlinear systems under sensor attacks. This is a joint work with Henrik Sandberg and Joao Hespanha. The problem that we address in this paper is a state estimation of a nonlinear system where we have n sensors, and a subset of these sensors may be corrupted. This is captured by the additive signal, AI, which is unmeasured and potentially unbounded. For this reason, we call this signal AI the attack signal. For the sensors that are not under attack, the signal AI is 0 for all time. We also assume that the set of uncorrupted sensors is unknown and remains constant. Our objective is to estimate the state X given that m out of n sensor measurements are under attack. Before we proceed to the results in our paper, I'd like to point out several related work in the literature. We start off with reference 1 by myself, Masashi and Joao in 2015, where we looked at linear systems in continuous time. In this paper, we extend the ideas in this reference 1 for nonlinear systems with non-restrictive assumptions. Another closely related work for linear systems was done by the authors of reference 2 in discrete time. The necessary and sufficient condition provided in reference 2 agrees with the one provided in 1. However, the algorithm proposed is different, as the authors in 2 employed tools inspired by coding theory due to the discrete time nature of the system considered. Another piece of work is done by the authors of reference 3, which extended the ideas in reference 1 for a class of nonlinear systems in discrete time. I would also like to mention reference 4, which provides a novel secure state estimation method for nonlinear systems under sensor attacks, with the caveat that the system has to be uniformly observable. In this work, we relax the uniform observability condition for nonlinear systems. The main idea behind this work is based on our idea for linear systems in this reference here, where the necessary and sufficient conditions are that the number of sensors, n, has to be strictly larger than twice the number of attack sensors. Secondly, we also require that for every combination of n-2m sensor measurements, we can design an observer which is robust with respect to the combined attack signal vector, aj, whereby aj is the stacked vector of attack signals indexed by the index set j. In the case for nonlinear systems, we only obtain a sufficient condition with a modified definition on the observability of a system under m sensor attacks. What we mean by that is that for the nonlinear system we consider is for any initial condition and any index sets IA and IB with not more than m elements, which indexes the attack vectors A and A bar, and for a common measured input signal, W, we compare the output trajectory of this system, which is initialized by one initial condition and the attack signal from the first attack vector, and we compare it to the output trajectory of the system generated by another initial condition and the attack signal from the other attack vector. Now we require that there exists an index set J with at least n-2m elements such that the norm difference between these two trajectories is upper bounded by a class K function of the norm difference in the initial conditions, and also lower bounded by a KL function that grows with the norm difference in the initial conditions but decreases over time. What this sandwich inequality here essentially means is that there must be at least one set of n-2m sensors for which at most one initial condition would generate a particular output trajectory. When this condition holds, we say that the system is observable under m attacks. In other words, there must be a set of n-2m or more sensors for which the state of the system can be reconstructed from the measured output and input. The resulting sufficient condition for a system to be observable under m attacks is, first, the number of sensors n has to be strictly more than twice the number of corrupted sensors. And secondly, for every index set J with at least n minus 2m elements, there exists another dynamical system, sigma J, for which if we provide a vector of potentially corrupted measurements, yj, and the measured input w, we can show that the error between the state of system 1 and sigma j satisfies an ISS property with respect to the attack vector aj, whereby aj denotes the stacked vector of attack signals ai indexed by the index set j. There are 2 points which I would like to highlight here. The first one is that condition where the number of sensors have to be strictly more than twice the number of attack sensors is consistent with the results for linear systems and a class of nonlinear systems in the related works discussed earlier. This condition also means that when we know that m number of sensors may have been attacked, it effectively disables twice the number of attack sensors. The second point which I wish to discuss is a dynamical system required by condition 2 is essentially an observer with an ISS property. Note that if we have chosen an index set J which does not contain any attack sensors, the second term is equal to 0, and we're left with a globally asymptotically stable error system, EJ. It is using this observation that we have constructed a 2-tier secure estimation algorithm presented here. Now the algorithm is as follows. Given the measurements from n sensors, we generate all the n minus m combinations and all the n minus 2m combinations of y under the assumption that we can design observers which are ISS with respect to the relevant attack vectors. We compare the state estimates generated by each observer. Pi s is our consistency matrix, which compares each state estimate from the first group of observers with the state estimates generated from the second group of observers whose index is a subset of the index in the first set. Recall that m denotes the number of attack sensors, so there must be one set S which indexes the attack-free measurements. For this particular set S, the state estimates for which we'll compare with from the second group would also be generated from attack-free sensors. And by the ISS property of the observers, the state estimates will be consistent with each other. Therefore, based on this observation, we choose the state estimate to be the one given by this particular observer. By this argument, we can prove that this secure state estimation algorithm provides state estimates which converges to the true state for all initial conditions of the system 1 and the observers in the presence of potentially unbounded attack signals AI. So far, we've provided a framework for the estimation of states in the presence of sensor attacks. Let's take a closer look at how can this be constructive for a class of nonlinear systems. This particular class takes a Lua form where we have a linear part and a nonlinear part. We assume that these nonlinearities are slope restricted, which means that these nonlinearities have to fall within this shaded region right here. Now suppose that the number of sensors n is strictly twice the number of attack sensors m, and for every index set j with n minus 2m elements, there exists positive definite and symmetric matrix P, positive scalars nu and mu, and observer matrices k and j, where we have designed the observers to take this particular form. Note that it has taken this particular form whereby the first part is a copy of the actual dynamic of the plant 1, and we have injected output injection terms in as follows here. So there's one here and one inside the nonlinearity. The design boils down to an LMI which is written in a paper. If the LMI holds, then system 2 is said to be observable under M attacks, and we can employ the secure state estimation framework we described earlier. An application area where the security of sensor measurements is highly relevant is in smart grids. On this slide, we're looking at a power distribution network where we have end customers equipped with renewable energy sources. Hence, this is not the traditional setup where each customer is only a consumer of power, but also a producer of power. Each customer is equipped with a DC to AC inverter, which is the controller that ensures that each customer injects the appropriate amount of power back into the grid based on the consumption of every customer, such that the voltage received by each customer, VI, is within a safety margin. Now, this reference voltage V bar is communicated to each controller from the substation, which also measures the received voltage VI. In other words, the substation is our monitoring center, which ensures that all the voltages VI are within the safety margin and raises an alarm if the safety margin is violated. This showcases the importance of having reliable measurements, as the monitoring signal may raise false alarms if it receives corrupted measurements. It turns out that in this particular setup, and with the controllers usually used in practice, falls in the class of the nonlinear systems for which we've studied a few slides earlier. Hence, we can secure the monitoring of this power distribution network using the secure estimation algorithm proposed in this paper. In conclusion, we have provided a sufficient condition for the observability of a nonlinear system under sensor attacks. The condition requires the number of sensors to be strictly twice the number of attack sensors, and requires the construction of observers, which are ISS with respect to the appropriate attack vector. We provided a two-tier estimation framework and showed that this is constructive for a class of nonlinear systems. Finally, we discussed how this secure state estimation algorithm is highly relevant in a smart grid system. With that, I thank you for your attention, and I'll be happy to address any questions you may have. Enjoy the rest of this virtual CDC.